It's good to understand that. Okay, so, like last time I showed you an example, right? X squared continuous at 0. And then I asked, does the same delta work for x equals 1? And it certainly doesn't, right? But then you could ask, does the delta for x equals 1, now does that work for everything else? And it turns out no. So let's do an easy case, right? X squared on r, right? Why is this not continuous? So before that, let me erase this. Let me sort of define what continuity is and uniform continuity. So F continuous, so let's define continuity first. S, so obviously it has to be in the domain of F, if and only if for each x naught in S, right? And epsilon bigger than 0, there exists delta bigger than 0. So here delta depends on x naught and epsilon, right? So if you move your point, your delta can change. So that basically if x minus x naught is less than delta, f of x minus f of x naught is less than epsilon. Now, f is uniformly continuous, right? On S, if and only if for all epsilon bigger than 0, there exists delta bigger than 0, such that for all x, y, and s, so this is the part, right? There's a delta that holds for every point you choose. And x minus y is less than delta, then f of x minus f of y is less than epsilon, right? So let's sort of go over, maybe say x squared on r, right? Let's see why this is not uniformly continuous, right? So if it was, then, it has to hold for like epsilon. What's your favorite number? Let's say 2. So it has to hold for all epsilon. So let's just pick epsilon equals 2. Then there exists delta bigger than 0, such that for all x, y, my set S is r, in r, and x minus y less than delta, f of x minus f of y is less than 2, right? So this is just reformulation, x squared minus y squared, right? In our case. So what you do is, you just choose a y, right? Give me a point y in here. You can take anything, but the common choice is just divide by 2. So y is x plus delta over 2. So this is certainly in here, right? It satisfies this because it's only delta over 2 away from x, right? So if you look at this, right, and then x plus delta over 2 squared, what is this? So the x squared cancels, and then you get 2 negatives. So you just take that out, and then you should get delta squared over 4 plus x delta, I believe, right? And this has to be less than 2, right? But this can't happen, right? Because, delta's fixed, right? So there exists delta, but it has to hold for all x and r. So you could certainly choose x. So delta squared over 4 plus x delta is bigger than 2, right? That's certainly possible. So you see that this function is not uniformly continuous, right? It depends on the point of x, right? If you choose x, right, large enough, this thing will not hold. So now, is everyone good so far? Okay. So now what about x squared on, let's say 1 to 10, right? So it turns out this is uniformly continuous because let's do scratch work. I need to somehow bound this, right? But this is x minus y, x plus y, right? Now I have control of x minus y, right? I mean, by definition, right? I can make x minus y small. Now, x plus y, maybe not, but if I'm on 1 to 10, what is the biggest this can be? What is the biggest x plus y can be? Anyone? Yeah, 20, right? So this is last equal to 20 x minus y. So hopefully you know what to choose, right? Let epsilon be bigger than 0. Choose delta equal to epsilon over 20. Then if, this is for any point, x minus y less than delta, I have x squared minus y squared is less than 20 times x minus y, which is less than 20 times epsilon over 20, which is epsilon. So you see here that it's uniformly continuous, right? It never depended, like I made no choice of x and y, right? As long as x and y are close enough, this will hold, right? I'm not choosing any specific value of x, right? As long as they're within delta, it will always hold. So is everyone good so far? Okay. So you see here, right? What's the difference? This is x squared on r and x squared on 1 to 10. So it's actually, I forgot, I actually didn't copy this down, but it's not this. Sorry, give me a moment. Yeah, continuous function on a closed interval is uniformly continuous. So so basically it's a generalization of this theorem. Continuous functions on closed intervals a to b are uniformly continuous on AB, right? So an example would be like x squared, right? X squared on 1 to 10 was uniformly continuous, right? But not on R, right? Okay, so let me just, I'm not sure if you're allowed to use this. It certainly will make things maybe a bit easier, but functions with bounded derivatives are uniformly continuous. So by, are uniformly. So let me just put a, how should I say this? Quotes, yeah. So quote would mean, ask professor if you can use this, because we never really define derivative, right? I mean, we only define a continuous function and uniformly. We never reached the chapter for derivatives yet, right? But the idea is, but you all know this, right? So the idea is like NBT, right? If basically says f of x minus f of y is equal to f prime of like some value c times x minus y, right? So this is MVT, right? And then if your derivative is bounded, right? Let's say it's bounded by m, then you're done, right? You want to estimate this and is less than m times x. So sort of like here, right? I'm less than 20 times x minus y. And then so from here, you just choose delta is like epsilon over m. And then you get uniform continuity, right? So so a priori, so I'm not sure if you're allowed to use this, but if you can, might at least for the quiz, I'm not gonna check what you use, right? So if the derivative is bounded on whatever interval, then you're golden. So okay, now continuing on, but it's not true, right? So the opposite is, so like there are functions with unbounded derivative that are uniformly continuous. Right, so the classic example, right? So don't just say not uniformly continuous because derivative is not bounded. Yeah. So the classic example is f of x is root x, right? On, I don't know. I mean, on 0, you can even make it 0 to infinity, right? So the reason, I mean, you can take the derivative, right? You know what it is, power rule, and you're going to see it blows up as you go close to 0, right? Because it's 1 over 2 root x. So, but this function is actually uniformly continuous. So why? It's basically from this, right? I wanna, you know, scratch work. I wanna scratch. I wanna, you know, bound this, right? But what is the square of this? The square of this is root x minus root y, root x minus root y. Now this is bounded by, if I just change, since everything is positive, change this to plus, and now this is x minus y, right? So it's clear that if you let delta be epsilon squared, you're golden, right? Because, so let epsilon bigger than 0, then if x minus y is less than delta, which is epsilon squared, you have root x minus root y squared. From our scratch work, less than this, which is less than epsilon squared. So if you square root, you get that it's less than epsilon, right? So this function is uniformly, and it's clearly, I mean, I could have just made this include 0. I don't think it matters. But you see that here, right? I guess if I include 0, the derivative is not direct. It doesn't make sense at 0, but you know, it is uniformly continuous on 0, including 0 to infinity, right? By this proof. So be careful, right? Don't just say derivatives unbounded, so not uniformly continuous. Okay, is everyone good so far? Everyone sort of understand how uniform continuity works, right? The idea is you need to basically get something like x minus y, right? It shouldn't depend on what x and y are. The only thing that matters is x and y are close. Okay, so let's move on. So why do we study uniform continuity? It's because it's nicer than continuous functions. So have you ever wondered if I gave you a sequence, Sn converging to S, and a function on R, you know, you can ask, does f of Sn, you know, is basically that, does this go to I guess the better way to say it is, does f of Sn converge? Yeah. Right. And if so, you know, what does it converge to? And even for continuous functions, right? This is not true because you could take f of x as 1 over x, and you see that 1 over n goes to 0, so this is my Sn, this is my S. But then f of Sn is 1 over n, which is n. And this sequence diverges, right? It diverges to like infinity, right? So you don't want it. So in a sense, you know, it still goes to like f of 0, right? Because if you think of like f of 0 is sort of like infinity, but you see like it doesn't converge anymore, right? So it turns out that for if F uniformly continuous, Cauchy sequences map to Cauchy sequences. Let me to make it more clear. Has image is Cauchy as well. Right, and in the case you're in R, Cauchy is the same as converging, right? So obviously, from here you see that 1 over x is not uniformly continuous on 0. Let's just do 0, 1. Yeah. I mean, because if it was, the sequence n would be Cauchy, right? Right. Because 1 over n is clearly Cauchy. 1 over n converges, right? So it's saying the image will be Cauchy, which is not. But let's just prove it, right? So how do you prove it's not uniformly continuous on 0, 1? Right, so I mean, let's let epsilon, I don't know, what number do you want? Let's do 1. Then assume it is uniformly continuous, right? Then there exists delta such that, minus y less than delta. 1 over x minus 1 over y is less than epsilon. So I mean, from here you sort of get y minus x over xy is less than epsilon if you combine denominators, right? And I mean, from here y minus x is just x minus y, right? Because we have absolute value. So this thing, right, is certainly, less than 1, sorry. So I know that x minus y over xy, this is less than, so, sorry, I'm not trying to prove it's uniform. So let's choose a specific y, right? So again, I'm going to choose y equals, so I want to prove it's not, right? So y equals, let's just do the same thing. So this thing is what now? So this thing is x minus, so I get delta over 2. The negative doesn't matter because I have absolute value. And then x times x plus delta over 2. And this is supposed to be smaller than 1. But what you're going to see is for x small, right? The denominator goes to 0, right? Because you have a factor of x. So for x small, this thing is gonna blow up, right? It's gonna be bigger than 1. I mean, I'm pretty sure you could just say this. So you see, it's not uniformly continuous. Okay, is everyone comfortable right now? So we're gonna do maybe. Okay, let me just. Whoa, a lot of people. Okay, so let's move on. So let's just do an example from the book, and then So from here, let's do something more theoretical, yeah? So let's do 19.4a. Yeah, prove if F uniformly continuous on a bounded set, then F is bounded on S. So F uniformly continuous on bounded set S, right? So prove F is bounded function. Okay, any ideas? So right? So f is bounded. So let's assume it's not, right? Then what can you tell me? So can you construct, so let's use the sequence part, right? F must map, you know, Cauchy sequences to Cauchy sequences, right? So let's start forming a sequence. What does it mean that it's not bounded? Well, it means that there exists x1 in S such that f of x1 is bigger than 1, right? Because if not, then it's bounded, right? It's bounded by 1. And then there exists x2 in S such that f of x2 bigger than 2, right? And then xn in S such that f of xn is bigger than n, right? Okay, what's the next step? So we're almost done, right? Because if the xn's converge, you see f of xn does not converge, right? It's the sequence n, right? It clearly goes off to infinity. So if f was uniformly continuous, it should take convergent sequences, which are Cauchy, to convergent sequences, right? So you see here, we're almost done. We just need xn, we just need xn or some part of xn to converge. So does anyone see the next step? So what do you know? So this sequence xn is in S, right? And what do you know about S? S bounded. So what can you tell me about bounded sequences? There was like a lemma for that, right? Yeah, convergent subsequence, exactly. So choose, there exists x and k such that, I don't know. How should I denote the limit? X tilde, right? But f of x and k does not convert because this is a subset, right? So this is bigger than nk, but the index always, there's infinitely many terms, right? So this is still gonna go off to infinity, and that contradicts the fact f was uniformly continuous, right? Because if it was uniformly continuous, every Cauchy sequence has image that is Cauchy. In particular, it can't diverge, right? So yeah. Okay, is everyone clear so far? Okay. So let me just go over the two of them. I mean, I know the professor probably. So I'll just talk about it, yeah. So from here, let's see what we get. Yeah, see, like part 2, problem 2, the derivative is bounded. Let me think, is it bounded? Yes, because limit x goes to infinity. So you have 1 over 2 root x ln x, and root x certainly goes faster than ln x. Yeah, so derivative should be bounded. So I think problem 2 is easy if you could use the fact derivative is bounded, right? Because if you think of product rule, right here, it's 1 over 2 root x ln x, right? And root x grows faster than ln x, so this thing will be bounded. And then the product rule, it's you get root x over x, which is 1 over root x, and 1 over root x is bounded on 1 to infinity, right? The only time it's unbounded is if you go to 0, and you clearly avoid 0. So it's a fast proof if you just use mean value theorem. But yeah, okay. So but let's go over this thing, right? I'll just talk about it, and then all of you can write it. So A, B, B. Okay, so I'm assuming B is a number between A and C. So I have okay, so I'm just gonna give you a picture proof, and then you write it yourself. So there's a delta 1 that works on here, right? Because it's uniformly on continuous on AB. So problem is uniformly continuous on AB, and BC show uniformly continuous on A to C, right? And then there's a delta 2 that works for this, right? So obviously you're gonna let delta be delta 1 or minimum of delta 1. Why do I keep writing the fractions? Okay, the minimum, right? And what you're gonna see is you're gonna choose your delta. Sorry, I'll call. Let's denote this something else. Let little m be the minimum. Then we're gonna let delta be m over 2. Yeah. So the reason for this is, what's the only issue we see here? It's if what's the only difference between this and these two? It's if one point is here and the other point is here, right? But you see that if this is the case, right, and they are m minus 2 apart, then let's call this x and this y. Then x minus y is less than or equal to x minus b plus b minus y, right? Now this thing is less than what? Delta is less than m over 2, right? So since it's less than m over 2, the how do I say it? You can use uniform continuity on where's x, a to b, and then this thing is less than m over 2. Yeah, actually I'm not even sure if you need the m over 2, but the idea is this, right? And then you use uniform continuity on, oh sorry, maybe you don't even need the m over 2. Let me think. Yeah, you don't need this, but what I guess what I meant was, you sort of say, let me think. Yeah. Okay. Great. So I guess what I want to say is, we want to somehow bound this, right? So this thing, choose it for epsilon over 2, and this thing for I want epsilon over 2. So basically, there exists delta 1 that holds for epsilon over 2 and epsilon over 2. So then when you do this, you do f of x minus f of b plus f of b minus f of y, right? And then this is just this, right? Sorry, I mixed up domain and image for some reason. So because this is less than m, this thing is less than epsilon over 2, right? Because m was the minimum, right? So if you're less than delta 1, you're less than, if you're less than m, you're less than delta 1. And then from here, we chose it for epsilon over 2. So this is less than epsilon over 2. So it's like less than epsilon. So, I mean, that's the only, I mean, because if x and y lie in the same one, you're done. I mean, you're done by like, you know, this part, right? Or this part. So really the only case you need to care about is if like x and y lie, you know, one of them is in one interval and the other one's in the other. Okay, everyone clear so far? Hopefully. Okay, I'm just gonna go over one more and then let's just call it a day. So suppose f of x is on negative infinity to infinity and limit x goes to plus minus infinity of f of x is 1. Prove f is uniformly continuous on negative infinity to infinity. Okay, so f continuous on infinity and limit. So this just means this, I think. I think that's what she meant. Like when she puts plus minus. So what can anyone tell me? What does it mean for limit x goes to infinity to be 1? So if the idea, let me just write idea and then I'll write, this one's not that bad. So the idea is past a certain point, right? You know, if I pass a certain point, this thing is close to 1, right? And then from here, like past a certain point, this thing's close to 1, right? So if you could show being close to 1 means uniform continuous, you're done, right? Why? Because if I call this, I don't know. Well, what do I want to call it? I don't know. Let's just make it the same number. Like, I don't know, a to b, right? It's enough to show uniform continuity on like negative infinity to a and b to infinity. So why? So question, why do I not need to show uniform continuity here? Anyone? If you've been paying attention in the beginning of the discussion. Why do I not need to consider uniform continuity on A to B? We talked before. Huh? Well, hold on. No. We're not assuming uniform continuity. We want to prove uniform continuity, right? The problem before we already have uniform continuity. Yeah. So the idea is here. It's just that theorem, right? Let me go back up, just so everyone can remember. It's when I did the x squared, right? Right here. Continuous functions on closed intervals are uniformly continuous, right? So if a to b is a closed interval, so it's uniformly continuous, right? So from here to here, right, is uniformly continuous just by the theorem. So all you need to do is show like the tails are uniformly continuous. Is everyone clear for this? Okay. So again, let's let epsilon be bigger than 0. But we have to figure out what this b and a are, right? So let's figure out what the b is. So we have limit x goes to positive infinity, f of x is 1. So this by definition means, since I have epsilon, for all epsilon 1 bigger than 0, there exists n1 such that for x bigger than n1, f of x minus 1 is less than epsilon 1, right? So choose epsilon 1 equal epsilon over 2. Then we're done, because in fact, we don't even need any deltas here. For any xy bigger than n1, right? So my b will be like n1. Yeah. Sorry. Let me. I skipped a step. So there exists n1, right? Such that f of x minus 1 is less than epsilon over 2. So this is epsilon 1, right? So now I'm choosing my b to be n1. So in fact, you don't even need delta anymore, because for any xy bigger than n1, that's why it's so cool. Like you don't even need them close together. They could be as far apart as you need. F of x minus f of y is less than or equal to, I'm skipping steps, but let me just not skip. So again, minus 1 plus 1 minus f of y, and then triangle inequality, right? And then this is less than epsilon over 2. This is less than epsilon over 2, right? So sorry, for x bigger than n1, right? So then you're done, because this is epsilon, right? And then it's the same process for, negative infinity, right? So you would get an n2. So similarly, let me just write similarly, get n2 on other side, right? So I'll let you write that up, just for practice. And then you say, so from the two above, you get, so uniform continuity, continuous on n2, or no, it's n1 to infinity, right? So n1, right? That's the thing I proved, right here. And then for you, try practice. You get uniform continuity from negative infinity to n2, and then by theorem, I don't know the number. By theorem, n2 to n1 closed interval, and so let's go back to the theorem, right? So continuous functions on closed intervals are uniformly continuous. So that is where we are using the assumption of the problem right here, right? F continuous on negative infinity to infinity. So in particular, you're continuous on like n2 to n1, right? So by theorem, n2 to n1 closed interval, and F continuous on n2 to n1. So F is uniformly continuous on n2 to n1. Okay. So that's actually all I had for today. So let me just say, quiz is on uniform continuity, right? You use whatever method, right? For the quiz, you can use the fact that if your derivative is bounded, like it's uniformly continuous. So, or you could just prove it by hand. Anyhow, is everyone good? So again, let me just say Thursday would probably just be office hours, right? Last minute questions. So I think your finals on Monday, if anyone can confirm. Final should be Monday. So it's coming up. So study hard.